Well, hi everyone. Hope everything is going well in your world. Welcome to week 3, Business Maths and Stats. We're looking at graphing, solving simultaneous equations today. So I'm going to, let's go straight to the subject guide, which is our our roadmap for a study. It's important for us to follow this carefully, both teachers and students each week. So what will we be doing in class? We're going to be plotting and interpreting straight line graphs. We're going to be solving some simultaneous equations today and also in class. And particularly in relation to break-even analysis, which is a topic coming up for us, a very practical topic, and also comes up in management accounting, or sometimes called cost volume profit relationship. Now we're looking at 2 chapters again this week, so I'll probably break the recording into 2 parts. We'll do chapter 3 first, follow on with chapter 9, so you can break it into two sessions. I hope that they're less than 30 minutes each. That's my goal. I trust that that will happen for us. Keep looking at your guide for information about any assessments coming up, and we'll sort this one out in class with you this week as well. Hopefully by now you've done some practice from last week and are feeling pretty confident to face that worth 10%. So let's launch in and make a start on today's work. So, excuse me, some fundamental stuff here is, look, you would have covered some of this in your schoolwork. You would have come across algebra, and possibly even now it's being done in primary school, perhaps. Where algebra is really helpful, the mathematicians worked out very early on that if they allowed some symbols to some unknown quantities to be part of their formulas, they could solve for those unknown quantities. And so there are certain terms in our expression, 12, 3.5, 5 over 8, or pi. We're going to have a little look at pi, have a bit of fun with pi today for a few minutes. And but each one of these are constants. And but a variable is something unknown. So we'll put a little, an ABC, an XYZ, something in there to help us solve problems. A lot of people use, they use X and Y, but sometimes if you're looking for price, you might call P for price. You might label S for selling price, L for labor, M for machine hours, whatever you're trying to solve. It doesn't really matter what you call it. The end result's what you're looking for. So here is an algebraic expression where we've arranged a group of terms. A term is an expression that's separated by some sort of mathematical operation here, a minus and a plus. So we've got x cubed as a term, 3z squared is a term, and they gathered together to form an expression, I guess a formula if you like. Now, the degree of the expression is all about the exponential. So this particular expression here, 3x squared, it makes it a quadratic or a second degree expression. And just a couple of other key terms of jargon, the coefficient is the number that is multiplied by the variable. So the term 9xy has a coefficient of 9, the constant. Often the slope of a curve, when we have a look at some of our lines later on, we call that the coefficient. It's the slope. So as x increases, if x is on our horizontal axis and y is the vertical axis, each time x goes up by 9, where does y end up? Same with here. Y will become, y will become all of that. We'll need to put all of that into graph it. So later on, we'll be graphing terms like these. At some point down the track, we look at correlation coefficient. And so we'll just have a quick intro to that concept as well. So here's my x-axis, for example. Here's my y-axis. And I've got 2 things I'm trying to study. I'm trying to work out, is there a relationship between the number of hours a student might study and their potential test results or exam results? And one would expect that the more hours you put in, the better you know your work. And you would expect there to be this upward trend. As X is increasing, so is Y increasing. The results are getting better the more hours we put in. So we put a range, we gather the data, and then we plot it. So to plot this particular point here, this student did 1 hour's worth of study and they got a result of 30%. So we'd go down here and find one and we'd go up. So that's that particular spot, 30%. Someone else did 1 hour and they got 20%. So one and go up to 20%. One more did 1%, 1 hour of study and got 15%. So away we go, 1 up to 15. And we plot all of the points. And then we start to see how they're gathered together. And from this graph, it's not a perfectly straight line. There is some variation. The dots are varying from the line, but we can see there does seem to be a correlation between our X variable and our Y variable. And it's fairly strong. The closer those dots are together, the closer the correlation. More of that coming up in a few weeks' time. Here's a strong negative correlation. This time we're wondering about, is there a relationship between the number of drinks of alcohol consumed and the score that someone might achieve in a driving test? Again, one would expect this is a negative correlation. As this value is increasing, this value is decreasing. It's sloping down to the right. Our slope is negative. As X is increasing, Y is decreasing. And that is sort of what we'd expect, a pretty strong negative correlation. More of that, as I said, coming up soon. But it's a quick intro to how we might use straight line theory and graphs to get our heads around a concept that we're studying. So an equation is a statement where we make perhaps two expressions and we try and solve for it. So a linear equation, for example here, y equals 2x plus 7. The slope of this particular line is 2. Every time x goes up 1, y will go up by 2. The change in y over the change in x is the slope of the line. And it's a straight line, or sorry, it's a straight line. Yes, it's not exponential. It doesn't have a curve or a kick in it because x is to the power of 1. So anytime a variable is just to the power of 1, we know it's a straight line. The moment we get anything greater than 1, we'll get a kick in the curve. It'll bend up. As x increases, y will exponentially increase. So we're going to look a little bit in a few minutes' time at solving simultaneous equations. Let's do that. Coming up in the next couple of slides. Here's an example of what we were just talking about from last week. Our simple interest formula is a straight line. There is no exponential on the time. So the accumulated value equals the value today outside of 1 plus the interest rate times time. No exponential there at all. So if we were to graph it, it doesn't look like a straight line, but believe it or not, that is a straight line, the grey line. And we'll compare it with the compound interest formula. The future value equals the present value outside of 1 plus the interest rate, and here it is, to the power of n. So as the terms increase, if that was n equals 30, the period's at 30 years or something like that, we're getting this kick in the curve, starting off when x is 1, squared, cubed, fourth, etc. And as our years go up, we get up to 20, we'll get this kick, and it's just going to continue on this upward bend. We'll actually, in class, be having a look at how to calculate these. Well, from last week, we would have done some. We'll be doing some more as we go through the course. So let's have a look at a couple of simple formulas, perhaps. This one here, the formula for a circle, I want to just spend a couple of minutes on pi, just for fun in a moment. But the mathematicians worked out that the area of a circle happens to equal pi. Don't worry about what pi is just yet. We'll look at that in more detail in a sec. Pi times the radius of the circle squared. So we can prove that to them. We can prove the mathematicians got it right. and they did. But what if we wanted to make R the subject of the formula? So we want to get used to being able to rearrange a formula to find what we want to find. I mean, yes, we can plug in what we do know and solve it that way, but let's rearrange it as it is. Let's imagine we wanted to make R. So it's pi times R. So if we want to leave R on its own, we're going to need to divide both sides by pi. So once we divide this side by pi, pi will cancel out. Divide this side by pi, and we'll end up with R squared equals A over pi. And then the next thing to do is say, well, if I want to leave R on its own, I need to find the square root of this side and find the square root of that side. So when I find the square root of A on pi, basically I'll be left with R on its own. The square root of R squared is R. So we're left with R. And then I find the square root of that A over pi. So I'm just letting you use your imagination there, but just get used to, whatever these two terms are multiplied, so we've got to divide to leave. Which one do you want to leave on its own? Then divide by the coefficient of that term, and you'll solve the question. So hopefully that's straightforward for you. More you can ask questions. We'll work through those in class. So what if we want to simplify an expression? Well, when we've got two like terms, 5 times something minus 3 times something, we're left with, we can group those together and say, well, that's 2x. Can't do anything left with the 4z, so we'll be left with 2x plus 4z. What about expanding the bracket? Sometimes we need to do that. So each term inside the brackets, to make it work, has to be multiplied by the term outside the brackets. So this becomes 2 times 3x plus 2 times 4y, 2 times minus 1 equals minus 2. So multiplying that out, we get 6x plus 8y minus 2. So we've removed the brackets. And so hopefully that's a technique to help us move on and solve questions from time to time. Rearranging formulas, expanding brackets, all that sort of thing is an important mathematical tool. Gets a little trickier here where we've got two expressions with two parts in the brackets. So let's try and multiply both of these expressions. Essentially, we've got to multiply both parts of the second expression with that and both parts of the second expression with the 2. So doing it longhand, it becomes 3x times 2x minus 1 plus 2 outside of 2x minus 1. Let's expand the brackets. 3x times 2x becomes 6, and it's x squared. X times x is x squared. Minus 3x times minus 1 is minus 3x, plus 2 times 2x is 4x. 2 times minus 1, minus 2. Can we? Yes, we can simplify this a little bit. We've got two terms that are similar. 4x minus 3x leaves me with x. So simplifying the expression now, 6x squared plus x minus 2. Solved. What about solving linear equations? So imagine we've got this equation here, 9x minus 4x equals 3. Oh, sorry, just make sure. Yeah, here it is. Here's the original. 9x minus 27 equals 4x plus 3. So we've got to gather the like terms. So what we would need to do is subtract 4x. Whatever you do to one side of the equation, make sure you do it to the other side and everything will be fine. So we'll subtract 4x from this side of the equation, 4x from this side of the equation, and that 4x minus 4x will cancel out. So we'll end up with 9x minus 4x on this side of the equation. Now we want to get rid of this 27, get it over here. So we'll add 27 to both sides, leave the x's on one side and all the constants on the other. So add 27 to both sides. That'll cancel out the 27. 27 plus 3 equals 30. 9x minus 4x is 5x. Now we can solve. Divide. To leave x on its own, divide both sides by 5. That will cancel out, and we got an answer, x equals 6. So the rule that you probably used when you were at school is that as you cross the equal sign, the expression changes. So my -4 comes over here, becomes a +4. My -20 jumps the equal sign and becomes a +20. That's fine. It works, but you do need to be careful that when it's a little bit of a shortcut. If you're worried, just go longhand, just say, no, I'm going to add 4x to both sides. I'm going to add 4x to both sides. I'm going to add 20 to both sides. I'm going to add 20 and it will cancel out. So longhand or take the shortcut method. Just be careful that you end up, when you start taking shortcuts, that you don't accidentally forget to change the sign as it drops over the equal sign. So let's solve some simultaneous equations. Here's one method. One method is this like subtraction method rather than using, and I'm going to get back. I told you I'd talk about pi. We'll talk about pi in a moment. One method is to, subtract them, or we can rearrange the formula and substitute that into there. Let's do the multiplication method, and we're trying to find common denominator here between these two, and it looks like if I multiply this by 2, this whole equation by 2, I'll get 6x, and if I multiply this whole equation by 2, I will get 6x as well. And so so we can then we'll have the same expressions, if you like. So I'm going to multiply this by 2. 2 times 3x is 6x. 2 times 4y is 8y, 33 times 2 is 66. Multiply this by 3. 3 times 2x is 6x. 3 times 3y is -9y, and 3 5s are 15. And now I've got two equations that if I subtract equation 4 from equation 3, the 6x minus 6x will cancel out to 0, and I'll only be left with y values. Let's have a look. So here we go. We end up with, now I've got to be very, very careful here that you remember that it's 8y minus -9y. Like you might think, oh, I've got to add these two, and you might get, oh, that's -y. So I've got to be very careful that you get it right. It's because you've gone 6x minus 6x is 0. Now 8y minus -9y becomes 17y. So just be careful there. And 66 minus 15 is 51. So now I can easily solve for y, divide both sides by 17, and I've got an answer of 3. Pretty much what I've found is, where do these two lines cross? We did a tiny bit of this in week 1. We would find we've got a value for y. We could then plug that in to either equation now and find what x must equal. So if I put 3 into that 8y, I'll get 24, and I'll be able to find a value for x. So I could plot it on a curve. More of that in a moment. And here we are doing exactly that, putting that value for y into any one of the equations. He's decided to put it into equation number 1, 3x plus 4y. Well, we know y is 3. So we've got 3x plus 12 equals 33. Again, subtract 12 from both sides. 3x equals 33 minus 12 is 21. X must equal 7. So when x equals 7, y equals 3, we've now got a coordinate, a point that we could plot, and we're halfway to drawing a line if we wanted to graph that line. More of that in chapter 9. So here is the substitution method, rearranging the formulas and substituting it in. So let's see what we can do here. Let's see step 1. So that we've decided to rearrange equation number 1. We've decided to leave x on its own. So we're going to subtract 4y from this side, and we'll end up with 33 minus 4y. So we're going to get 3x equals 33 minus 4y. Then we need to divide both sides by 3 to leave x alone. So x will be, we had 33 over this side, so 33 divided by 3 minus, and we went, subtracted 4y from both sides, so it's going to be minus 4y divided by 3. So we'll end up with 33 divided by 3 is 11. So we end up with x equals 11 minus 4y over 3. So now we can grab that little expression there and plug that into equation number 2. We can say 2 lots of x. What's x equal? X equals 11 minus 4y over 3. So put that in for where x is. Minus 3y equals 5. So now we've got rid of the x. We've got like terms that these are only y's now, and we can solve it using the technique that we just saw a couple of slides back. We can expand the brackets. So 2 times 11 is 22. 2 lots of 4 is 8. So it's 22 minus 4y times 2 is minus 8y over 3. Minus 3y equals 5. Let's gather the like expressions. Let's subtract 5 from this side. So we'll end up 5, take 5 away, that disappears. We're left with 0. And 5 from 22 equals 17. And 17 equals, let's add these to get them on the other side. So we're going to add 8y over 3 is going to jump over here. And the minus 3y, we're going to add 3y to both sides. So we end up with 17 equals 8y over 3 plus 3y. So if you like, what we'll do now is we're going to multiply both sides by 3. That will get rid of this 3 fraction, if you like, and we'll have all the ratios looking good. So 17 times 3 is 51. We can then, if we multiply this expression by 3, that 3 eighths are 24 over 3. 3's into 24 leaves 8. So we're left with 8y. We've cancelled out, got rid of the denominator there of 3. Plus 3 lots of 3y is 9y. We end up with 17y equals 51. Y equals 3. And the good news now is we're exactly where we were back here. Y equals 3. So 2 different methods of solving simultaneous equations. You can pick whichever method you prefer. Sometimes this is easier, making the 2 equations, finding the common denominator. Sometimes it's awkward to try and find the common denominator, in which case you're left with it's best to know both methods. So if you need to use substitution, you can do that and solve the equations. You might remember from week 1, I referred to Nancy Pye, not her real name, but she's a very, very good teacher, very smart person. And she's got a whole swag of videos on YouTube. This one runs for 19 minutes. Interestingly, she uses, I'll let you try and solve the mystery. I know how she's doing it. You watch how she writes on the screen incredibly fast. You might say, how does she write so fast and backwards? Of course, writing fast is no problem. You speed it up. But how does she write so fast backwards? I'll let you work it out. There's a simple solution, a little trick that she's using there. But she will walk you through very, very carefully. So if you've got any issues with the last couple of slides and you'd like more examples, she really walks you through and which equations never cross. Is there an equation that will never have a solution? We talked briefly about that in week 1. Or is there an equation that has multiple solutions? So she'll cover that issue as well. So if you haven't had a chance, well worth looking at her work there. And here she is. So she uses 2 videos that are worth chasing up. Using substitution method, she again takes you through step by step by step. So if you're a bit rusty on algebra, she will walk you through nicely. By the end of this one, another 18 minutes, an investment of your time, hopefully everything will come flooding back to you and you'll be feeling confident about solving equations. But I wanted to just play. We've been talking about pi a couple of times. I just thought we'd just break and have a tiny bit of fun. before we solve a couple of questions. We're nearly finished this, but I just thought we'd have some fun with pi for a second. You know, I read someone made the quote this week, "I know every single digit of pi, just not in the right order." Not sure if you remember much about pi from your time at your studies so far. When I was at school, here's Excel having a bit of a crack at it's really 22 on 7 is a fraction that gets close to pi, but pi is an irrational number. It's totally irrational. And let's delve into why it's irrational, but this is the best estimate, and Excel will run it to 14 decimal places, 3.14, really, really early on. What happened when one of the experiments we did at school is it didn't matter if we had a garbage tin lid or a jam tin lid, we worked out that the ratio of the circumference of the circle was exactly the same, no matter how big, to the ratio. I'll get this right. The radius, the ratio of the circumference to the circle to the radius was exactly the same. Didn't matter if it was a garbage tin lid or a jam lid, whatever the size of the circle, it all came down to this pi. So if you know what the radius is, the mathematicians worked out, once we know what the radius is, we know it's always going to be pi, the ratio between the radius and the circumference. Then we can also work out what the area of a circle might be. It says, and whatever we end up with will be an approximation, because 22 on 7 or 3.14 is really only a very, very an approximation, because pi is irrational. And it's infinitely long. You can get some of this, if you want to chase it up, 10 surprising facts about pi from this website here. And here's a couple of little articles that I thought the most interesting parts of that article from 2018. Here is a record of how close the approximations were for pi. They'd worked out 4,000 years ago, they'd worked out that it's roughly 3. That's what they thought. So for a long, long time, they were working, when they're trying to build wheels for carts and whatever, they, I don't know, area of a silo or volume and whatever they were doing in calculating stuff, they just stayed with a rough ratio of 3. And then they started to get more decimal places, and the Egyptians are coming along here and doing a bit more mathematics. And let's have a look. It was, in fact, Sir Isaac Newton, 1665, few hundred years back, smart guy. He calculates pi to 16 decimal places. And then 1719, a French mathematician called Thomas Fanter de Lagny, he went to 127 decimal places. Not bad. Pen, paper, and a candle of a night time to work that out. And then here we go, the 1950s, we're starting to get computers and slide rules and whatever, and we're extending our knowledge of pi. Below are the first 2,800 digits of pi. I have a mate, I don't know why you would do it. He's memorized the first 30 digits of pi. Why would you bother? It's hard enough to remember your mobile phone number, let alone the first 30 digits of pi. Nobody's going to ask you to quote that, are they? 2,800 digits of pi. So you can see, in fact, from, if we were to jump up the top, we've got 3.14285. So already, when we look at the real thing, we get 3.14 is correct, but then the 22 over 7 starts to lose it. It becomes 159. And we said it's irrational. You can never get to the end of this number. It just keeps going and going and going. And the record for the most digits of pi memorized belongs to Rajveer Meena of Vellore, India, who he recited 70,000 decimal places on March 21, 2015. Why or how would you do that? I've got no idea. According to the Guinness Book of Records, that record still stands. But previously, Chao Lu of China, he recited to 67,890. I'm sure he thought in 2005, I've got this. Nobody can beat that. And yet along comes a guy 10 years later. And but can you imagine being the person who's got to sit there and check 70,000 digits that this guy is actually saying it in the right order? Or, you know, amazing from memory. So what the brain can do, it's amazing what you can squeeze into your brain if you have to. And these guys, there's a bit of an example of it. So I hope you found that interesting. If you want to chase it up, there's some other interesting facts about pi. Well, let's just finish up for this recording. So chase up Nancy Pi if you get a chance. I think she's worth listening to. Just from a teaching perspective, she explains things so well, so much better than I could. Let's have a look at some examples. So a couple of examples to finish with. This guy leaves his car for servicing, receives a combined bill for parts and labour. Total of the bill is $228. And somehow he knows that labour costs twice as much as parts. And we've got to find out, well, let's try and split the bill then between, well, how much did parts actually cost and how much did labour cost? So we could write a little formula. We could do trial and error. We could use GoalSeek in Excel, but hey, why not write a formula? And that will take a bit of the guesswork out of it. So let's let the amount charged for parts equal X. We don't know what it is, so let's just call it X. Therefore, if labour costs twice as much, the amount charged for labour must be 2X. Now we know that parts plus labour equals the total. So we put it together in an equation and we get X plus 2 lots of X, labour, equals 228. 3 lots of this unknown value equals 228. Sorry, 3 lots of the part cost is 228. Divide both sides by 3 and we've got the value for parts. So parts must cost $76 and labour must cost double that. So 2 lots of 76 equals 152, and both of those added together, you just double check, make sure it adds to 228, which it does. Problem solved. All right, so let's leave the video at that point. Maybe take a break and we'll come back for chapter 9.